Alright, now in this next video, we're going to give an example of one situation where calculating determinants is not so bad, right? We saw in the previous video that once we get up into 4x4 and larger determinants, it's very labor intensive to compute a determinant. And one of the things that if you kind of study the number of operations needed to compute these things, for large matrices, you don't want to compute the determinant via the cofactor expansion, even if you have a computer. It becomes computationally too complex to do it that way. There are just too many operations. You want to find ways of doing things more efficiently. Now, one way that's especially easy is if you're dealing with a triangular matrix. So a triangular matrix is one where all the entries either above or below the main diagonal are 0. Okay, so an upper triangular matrix is going to be one so for example, something like this: 3, 4, minus 1, 2, 7. So 0 is below the diagonal. Okay. That's what an upper triangular matrix looks like. Okay. A lower triangular matrix is one where you've got zeros above the diagonal. So you've got, 5, 2, minus 4, 9, 12, 3, 0, 0, 0, something like that. Okay. So the triangular kind of comes from the triangle, the upper triangle, or the lower triangle. This is where the terminology comes from. Okay, so it's a situation where everything either below the main diagonal is 0 or everything above the main diagonal is 0. Now, if you want to compute the determinant of a triangular matrix, it's dead easy because all you got to do is multiply down the diagonal. Okay, the determinant of this guy here is just 2 times 3 times 4. The determinant of this guy here, it's 5 times 2 times minus 4. Right? That's super easy. You don't have to worry about anything else. You just got to multiply down the diagonal. So, how do you compute a determinant efficiently? Well, we'll see that in the later videos. You calculate a determinant efficiently by first reducing your matrix to triangular form using row operations and then taking the determinant of that triangular matrix. Okay. In terms of the number of operations, in terms of the computational complexity, reducing a matrix to triangular form is much less work than computing a determinant via cofactor expansion, especially once the matrices start getting larger, right? Once you get to like 10 by 10, 20 by 20, 100 by 100, you don't want to be, you don't want to calculate the determinant of a 100 by 100 matrix recursively. That's ridiculous. Nobody wants to do that. It would be way too much work. You want to reduce your matrix down to triangular form and then multiply down the diagonal. It's much faster. Okay. So let's do a couple of examples and just so we can see why this theorem is true. Why is it true that if so let's say I do this guy, minus 7, 1, 3, 0, 12, 4, 2, 5. Okay. Why is the determinant just the product down the diagonal? Well, if I wanted to calculate the determinant of this guy, okay, the determinant of this guy would be what? Well, I'm going to expand along the first row. So along the first row, it's 3. The sign factor in the first row, first column is positive. 3 times 2, 0, 0, 1, 3, 0, 4, 2, 5, right? So I expand along the first row, I delete the first row, I delete the first column, I take what's left over, and then my other terms, I have 3 other cofactors, but they're all multiplied by 0, so I don't bother to do those. Okay, and then I expand along the first row again. 3 times 2, expand along the first row, so I delete row 1, column 1, right, and I get 3, 0, 2, 5. Okay, And well, that's a 2 by 2 determinant, so I could keep going, right? I could expand along the first row again, but you know, it's 2 by 2. We do 3 times 5 minus 0 times 2, so it's 3 times 2 times 3 times 5, which is just the product of the diagonal entries, right? So we get this because we can expand along a row where all but one of the entries are 0. This is what makes it easy. Similarly, if I wanted to do the determinant of, let's do an upper triangular example, minus 4, 1, 2, 1, 5, 0, 2, 1, 7, 8, 0, 0, 3, 9, 152. It doesn't matter what those numbers are. All right, 0, 0, minus 1, 12, 0, 0, 0, 0. Let's get rid of that last 2. 2. Okay. So if I wanted to do this determinant again, well, this time the smart money is on expanding along the first row, right? The Laplace expansion theorem says I can expand along any row or column I want. I expand along the first column, and that's going to give me minus 4. Well, it's going to be minus 4 times this smaller determinant there. How would I do that smaller determinant? I would expand again along the first column, and that would give me 2 times, well, this smaller determinant. How do I do that smaller determinant? I expand along the first column, 3 times, well, this guy, and that one I just get minus 1 times 2 because the other diagonal is 0 times 12. It's 0. Okay? And so we get our job. So 4 times 4, 48 in this case, right? Minus 4 times minus 1 plus 4, 2 times 2 is 4. That's 16 times 3, 48. Okay, I guess I should have done this one up here too, right? 10 times 6, 60. So if we've got triangular matrices, we're happy because determinants are easy for triangular matrices. So in the next couple of videos, we'll go over how to actually, reduce a matrix down to triangular form. So, how do we get our matrix down to triangular form? We use row operations, right? We use elementary row operations to create zeros. So we'll see how that's done in the next couple of videos.